Welcome to this problem walkthrough. In this video, we'll explore the exciting challenge of solving problem number 1952, 3 divisors. We'll break down the problem, examine different approaches, and provide a clear and efficient solution. Let's dive in. The problem asks us to determine if a given integer, n, has exactly 3 distinct positive divisors. A divisor of n is any number x such that n%x equals 0, meaning n is divisible by x without leaving a remainder. If n has exactly 3 of these divisors, we return true, otherwise, we return false. The input to the problem is a single integer, n, and the output is a Boolean value, either true or false. Let's look at some examples to better understand the problem. In the first example, the input is n equals 2. The divisors of 2 are 1, 2. Since there are only 2 distinct divisors, the condition of having exactly 3 divisors is not met, so the output is false. In the second example, the input is n equals 4. The divisors of 4 are 1, 2, 4. Here, we see that there are exactly 3 distinct divisors, so the output is true. These examples help clarify when the function should return true or false based on the number of divisors. In the third example, the input is n equals 9. The divisors of 9 are 1, 3, 9. Since there are exactly 3 distinct divisors, the output is true. Moving on to the constraints, the input number n is guaranteed to be between 1 and 10,000. This means our solution needs to handle both small and large values of n efficiently. Additionally, edge cases should be carefully considered to ensure the function behaves as expected for all valid inputs. Some important edge cases to consider include the smallest input, n equals 1, which has only one divisor, 1, so the output is false. For any prime number p, the divisors are 1, p, meaning there are only 2 divisors, so the output is also false. On the other hand, perfect squares of prime numbers, like 4, 2 superscript 2, 9, 3 superscript 2, or 25, 5 superscript 2, have exactly 3 divisors, 1, p, p superscript 2, so the output is true. Finally, for large inputs up to n equals 10,000, the solution must efficiently compute the divisors without exceeding time limits. These edge cases and constraints guide us toward writing a robust and optimized solution. To solve the problem of determining whether a number has exactly 3 divisors, the brute force approach is the most straightforward method to consider. The idea here is to simply iterate through all integers from 1 to the number n and count how many of them are divisors. A divisor is any integer that divides n without leaving a remainder. So, for each number I in our iteration, we check if n%i equals 0. If it is, we increment our counter. Once we've checked all numbers up to n, we look at the counter. If it equals 3, that means n has exactly 3 divisors, and we return true. Otherwise, we return false. While this approach is easy to implement and understand, it's quite inefficient, especially for large values of n, because it involves iterating through all integers up to n. This makes the time complexity O, n, which can quickly become impractical for large inputs. Furthermore, this method doesn't take advantage of any deeper mathematical properties of numbers, making it less optimal overall. Now, by leveraging mathematical insights, we can develop an optimized approach that avoids the inefficiencies of brute force. The key observation here is that a number has exactly 3 divisors only if it is the square of a prime number. This is because for such a number, the divisors will always be 1, the square root of the number, and the number itself. For example, if n is the square of a prime, like 9, its divisors are 1, 3, and 9. This means we don't need to check all divisors of n. Instead, we can focus on 2 main checks: first, whether n is a perfect square, and second, whether the square root of n is a prime number. To implement this, we start by calculating the square root of n. If the square root is not an integer, we can immediately conclude that n doesn't have exactly 3 divisors. If it is an integer, we then check whether this square root is a prime number. To test for primality, we iterate through numbers from 2 to the square root of n, ensuring the number isn't divisible by any of these values. If the square root is prime, we return true, otherwise, we return false. This approach dramatically reduces the number of calculations required. The time complexity is now O, sqrt, n, for checking the square root and O, sqrt, n, for the primality test, making it far more efficient than brute force. The optimized approach offers several advantages over brute force. First, it is significantly faster, especially for large values of n, because it avoids exhaustive divisor counting and focuses only on perfect squares and their square roots. By leveraging mathematical properties, we eliminate unnecessary computations, making the solution both elegant and efficient. This optimization is why we choose the mathematical approach as our strategy. The key insight that a number with exactly 3 divisors must be the square of a prime is the breakthrough that simplifies the problem and reduces the search space dramatically. However, there are trade-offs. This approach relies on mathematical reasoning, which might be less intuitive for beginners. Additionally, it requires a separate check for primality, but this is computationally manageable given the reduced input size. In contrast, the brute force method, while conceptually simpler, is far too resource-intensive for large inputs, making it impractical for real-world scenarios. By balancing clarity, efficiency, and scalability, the optimized approach stands out as the superior solution to this problem. To determine if a given number n has exactly 3 divisors, we first need to understand what a divisor is. A divisor is any number that can divide n without leaving a remainder. For example, when n is 9, its divisors are 1, 3, and 9, exactly 3 divisors. On the other hand, if n is 10, it has 4 divisors, 1, 2, 5, and 10, which means it doesn't meet the condition. One approach to solving this problem is the brute force method. The intuition behind this approach is straightforward: iterate through all integers from 1 to n and count how many of them divide n completely. If the count equals 3, we return true, otherwise, we return false. To implement this, we start by initializing a counter variable, typically set to 0, to keep track of the number of divisors we find as we iterate through the numbers. Once we initialize the counter, the next step is to loop through all integers from 1 to n to check for divisors. For each integer I, we check if n modulo I equals 0. If it does, I is a divisor, and we increment the counter by 1. After the loop is complete, we examine the final value of the counter. If it equals 3, the function should return true, indicating that n has exactly 3 divisors. Otherwise, it returns false. While this brute force method works, it can be inefficient for large values of n, as iterating through all numbers up to n is computationally expensive. To address this, we turn to an optimized approach. The key insight here is that any number with exactly 3 divisors must be a perfect square, and its square root must also be a prime number. For instance, 9 is a perfect square, and its square root, 3, is a prime number. This is because the divisors of a perfect square p squared are 1, p, and p squared. If p is prime, no other divisors exist. Building on this insight, we can optimize the solution by first checking if n is a perfect square. We compute the square root of n, rounded down, and verify if squaring it again equals n. If not, we can immediately return false, as non-perfect squares cannot have exactly 3 divisors. Once we confirm that n is a perfect square, the next critical step is to check if the square root of n is a prime number. A number is considered prime if it is greater than 1 and divisible only by 1 in itself. To check this, we loop through integers starting from 2 up to the square root of n. If any number in this range divides the square root of n evenly, it is not prime, and we return false. If no divisors are found, the square root is prime, and we return true, indicating that n has exactly 3 divisors. This optimized approach not only ensures correctness but significantly reduces the computational complexity compared to the brute force method. When analyzing the data structures and computational requirements for each approach, we find that the brute force method uses a simple counter variable to track the number of divisors. Since no additional data structures are needed, it has a space complexity of O(1). However, its time complexity is O(n), as it involves iterating through all numbers from 1 to n. The optimized approach, on the other hand, relies on arithmetic calculations and avoids the need for a full divisor count. It has a time complexity of O(n) for the perfect square check and O(n) for the primality test, making it significantly faster for large values of n. Like the brute force method, the optimized approach also has a space complexity of 1, as it does not require any additional storage. These improvements in efficiency make the optimized approach well suited for handling larger inputs. When solving this problem, it's important to consider edge cases to ensure robustness. For example, if n equals 1, it has only one divisor, so the function should return false. If n equals 4, it has exactly 3 divisors 1, 2, and 4, so the function should return true. For large values of n, the optimized approach is capable of handling the input efficiently due to its reduced number of iterations. To illustrate the algorithm, let's walk through 2 examples. First, consider n equals 9. We check if 9 is a perfect square. Its square root is 3, and squaring it gives 9, so it is a perfect square. Next, we verify if the square root, 3, is prime. Since it is divisible only by 1 and 3, it is prime. Thus, the function returns true. Now consider n equals 10. Checking if 10 is a perfect square, we find that its square root, 3, squared does not equal 10. Therefore, 10 is not a perfect square, and the function returns false. These examples demonstrate how the algorithm handles various scenarios effectively. This solution determines whether a given integer n has exactly 3 divisors. The function is3 iterates over the range of potential divisors from 1 to the square root of n, inclusive. For each I, it checks if I divides n evenly. If it does, I is counted as a divisor, and the corresponding factor n // I is also considered unless I equals n // I. If at any point the divisor count exceeds 3, the function exits early by returning false. At the end of the loop, the function checks if the total divisor count equals 3 and returns true if so, or false otherwise. This ensures efficiency by limiting unnecessary iterations and early termination when possible. The solution is optimal for small values of n as required by the problem constraints. This is the Java implementation of the LeetCode problem 3 divisors, number 1952. The solution mirrors the provided Python logic, iterating up to the square root of the input number and counting divisors. In Java, explicit type declarations and integer division are handled carefully. The function returns true if the number has exactly 3 divisors, otherwise false. The early exit optimization ensures the function stops counting once more than 3 divisors are found. Let's start with example 1, where n is equal to 4. First, we initialize our count variable to 0, which will help us track the number of divisors we find. Now, in the first iteration of our loop, I is set to 1. We check if 4 is divisible by 1, and since it is, we increment our count by 1, making the count equal to 1. Next, we verify if 1 is not equal to 4 divided by 1, and this condition is true because 1 is not equal to 4. This means that 4 is also a divisor, so we increment the count again, making it 2. Moving to the second iteration, I is now 2. We check if 4 is divisible by 2, and since it is, we increment our count by 1 again, bringing it to 3. However, since 2 is equal to 4 divided by 2, there is no additional divisor to count here. At this point, our loop ends because I has surpassed the square root of n. We then check if the count is equal to 3. In this case, it is, so we return true. The final output for n equals 4 is that the number has exactly 3 divisors, which are 1, 2, and 4. Moving on to example 2, where n is 9, we begin by initializing the count variable to 0 once more. In the first iteration of the loop with I equal to 1, we check if 9 is divisible by 1. This condition is true, so we increment our count by 1, making it 1. Then, we verify if 1 is not equal to 9 divided by 1, which is true, so we know that 9 is also a divisor. We increment the count again, bringing it to 2. In the second iteration, I becomes 2. Since 9 is not divisible by 2, the count remains unchanged at 2. Next, in the third iteration where I is 3, we find that 9 is divisible by 3, so we increment the count by 1, making it 3. Because 3 is equal to 9 divided by 3, we do not add any additional divisor. When the loop ends, we check if the count is 3. Since it is, we return true. The final output for n equals 9 is that the number has exactly 3 divisors, which are 1, 3, and 9. Now, let's consider example 3, where n is 10. As usual, we start by initializing the count to 0. In the first iteration with I set to 1, we check if 10 is divisible by 1. This condition is true, so we increment the count to 1. Then, we check if 1 is not equal to 10 divided by 1, which is true. Therefore, 10 is also a divisor, and we increment the count again, making it 2. In the second iteration, I becomes 2. We check if 10 is divisible by 2, and it is, so we increment the count by 1 to make it 3. Next, we verify if 2 is not equal to 10 divided by 2, which is true since 2 is not equal to 5. This means 5 is also a divisor, so we increment the count to 4. At this point, we notice that the count has exceeded 3, which allows us to exit early and return false. The final output for n equals 10 is that the number has more than 3 divisors, specifically 1, 2, 5, and 10. The goal of the function is to determine if a given integer n has exactly 3 divisors. To do this, the function iterates over all integers from 1 to the square root of n and checks if each number divides n without a remainder. If it does, this means we've found a divisor, and the function increments the count of divisors. Additionally, for each divisor I, the function checks the paired divisor n//i to ensure all divisor pairs are accounted for. The outer loop runs from 1 to sqrt n, meaning the number of iterations is proportional to the square root of n. Within each iteration, the divisibility check is a constant time operation, and the additional check for the paired divisor is also constant time. Importantly, the function uses an early exit strategy. If it discovers more than 3 divisors at any point, it stops the loop and returns immediately. However, in the worst-case scenario, the loop will still iterate through all numbers up to sqrt n. Now, looking at the total time complexity, in the worst-case scenario, the loop executes approximately sqrt n iterations. Since each iteration performs a constant amount of work checking divisibility and potentially counting up to 2 divisors, the overall time complexity is O sqrt n. However, in the best-case scenario, the function may terminate early if more than 3 divisors are found before completing all iterations. For instance, composite numbers with many divisors might cause early exit. Despite this, the big O complexity is based on the upper bound of runtime, which remains O sqrt n. Shifting to space complexity, the function only uses a few variables: count, which tracks the number of divisors, and the loop variable I. Each of these is a single integer, requiring constant space. Since no additional data structures or recursion are used, the space complexity is O(1). To better understand the efficiency, let's compare this approach with a naive solution. A naive method would count divisors by iterating through all integers from 1 to n, checking each one for divisibility. This results in a time complexity of O(n), because it performs checks for all integers up to n. In contrast, the optimized approach leverages the fact that divisors come in pairs. If I is a divisor, then n//i is also a divisor, so we only need to iterate up to sqrt n, and simultaneously check both divisors. This reduces the time complexity to O sqrt n, which is significantly better than the naive O(n). The mathematical justification for this big O analysis lies in the nature of the outer loop, which iterates approximately sqrt n times. Since each iteration involves a constant amount of work, the total runtime is proportional to sqrt n multiplied by O(1), which simplifies to O sqrt n. Finally, the space complexity remains O(1), as no additional memory is used beyond the loop variable and the divisor count. When solving the 3 divisors problem, there are common mistakes that can trip up many candidates. First, not accounting for perfect squares leads to a fundamental misunderstanding of the problem. Numbers with exactly 3 divisors are always the square of a prime number. For example, 9, which is the square of 3, has exactly 3 divisors, 1, 3, and 9. On the other hand, non-perfect squares like 12 have more than 3 divisors, making them invalid. Another pitfall is iterating through all numbers up to n and counting their divisors. This brute force approach is computationally expensive and unnecessary since the problem can be reduced to working with perfect squares and primes. Finally, implementing inefficient or incorrect prime checking methods can significantly slow down your solution. For instance, iterating up to north instead of the square root of n during primality checks can lead to a time complexity of n^3/2, which is impractical for large inputs. Another common challenge lies in handling edge cases. For example, small values like n equals 1, which has only one divisor, or negative numbers, which are invalid, can cause issues if not explicitly addressed in your solution. Additionally, relying on floating point arithmetic to compute square roots can introduce inaccuracies, especially for large numbers. This is because floating point precision is not always reliable when determining if the square root of a number is an integer. To avoid such errors, it's better to use integer arithmetic, such as checking if the square of the integer square root equals the original number. Properly addressing these factors ensures your solution is both accurate and efficient. Understanding the core insight of this problem is key. A number with exactly 3 divisors is always the square of a prime number. For example, if n equals p squared, where p is a prime number, its divisors are 1, p, and p squared exactly 3. This insight drastically reduces the problem space since we only need to consider perfect squares whose square roots are prime. To optimize, we can generate all primes up to the square root of n using the sieve of Eratosthenes, which runs in O(sqrt n log sqrt n, and then check for each prime whether its square is less than or equal to n. Developing this level of pattern recognition is critical for divisor-based problems, as it demonstrates a deep understanding of number theory. Additionally, during interviews, clearly explaining why you focus on perfect squares and primes is essential. It not only shows your problem-solving skills but also your ability to communicate mathematical insights effectively. Several related problems on LeetCode can help you build a stronger foundation for divisor-based questions. For instance, in LeetCode 204, Count Primes, you also need to generate prime numbers efficiently, often using a sieve algorithm. LeetCode 507, Perfect Number, tests your understanding of divisor summation, which is another important property to grasp. LeetCode 263, Ugly Number, involves factorization and divisors, requiring you to analyze numbers in terms of their prime factors. Finally, LeetCode 1979, Find Greatest Common Divisor of Array, while not directly related, emphasizes number theory fundamentals, which can strengthen your intuition for divisor-related problems. Solving these problems will give you a broader perspective and a stronger grasp of the principles needed to tackle the 3 divisors problem and similar challenges. There are several approaches to solving the 3 divisors problem, each with its own trade-offs. A brute force approach involves iterating through all numbers from 1 to n and counting the divisors for each. While simple, this method is highly inefficient with a time complexity of n squared. A more optimized solution involves pre-computing all primes up to sqrt n using a sieve. For each prime, you then check if its square is less than or equal to n. This approach is highly efficient, with a time complexity of sqrt n log sqrt n, but requires familiarity with the sieve algorithm. Lastly, a direct mathematical check can be used where, for each number, you determine if it is a perfect square and then check if its square root is prime. This method strikes a balance between efficiency and simplicity, especially if you already have a reliable primality test. Choosing the right approach depends on the constraints and your familiarity with these techniques. Great job! In this video, we tackled the 3 divisors problem and highlighted key concepts like divisors and efficient problem-solving strategies. Keep practicing, apply these lessons to similar problems, and remember, coding is all about persistence and learning. Thank you for watching, and we'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!